In this section, we're going to study a way to encode and even re-encode values to fit the problem 2 array indexing. The heart of this problem is to generate index values from the encoded ASCII characters. Characters are in a sequence, so this makes it easy because indexes also are in a sequence. The chars array holds 100 random lowercase letters, but it is clear that the smallest lowercase letter is A and the largest is Z. The rest fit in between. In decimal, the Unicode encoding would make the A 97 and the Z 122. All the numbers, including 97 and 122, in that range would represent A through Z. One possible approach is to define a counts array to keep track of each occurrence and use 123 elements, maximum index of 122 because Z is encoded as 122. So each time a letter shows up, we simply use that Unicode encoding as its index value. That works. However, the elements in range 0 to 96 are unused. Now, we don't immediately eliminate this as a possibility. In some cases, that's not a big problem. That's 97 integers. 97 times 4 is roughly 400 wasted. Not a big deal. But it represents perhaps either a misunderstanding or laziness or some other negative connotation to doing a problem this way. Again, not technically incorrect, but perhaps not well thought out. What we want to do rather is to re-encode the Unicode values in a range 1 to 26. Well, not quite. Since we're using arrays, we really should be doing it in the range 0 to 25 because that exactly matches indexing ranges. So to convert a code that represents a Unicode character, or ASCII, we can use those interchangeably, to range 0 to 25 inclusive, we can take the character in the chars array, such as chars sub I, and subtract from it the value A, represented here as an apostrophe, A apostrophe, which is a literal value that's encoded to the value 97. We could subtract 97, and that would show that we have some understanding of the actual value of lowercase a. I don't recommend using the constant 97, rather the character literal A, because that documents very clearly what we're trying to do. The final line of code to increment the count for each character would be counts sub chars sub I minus A increment. And we would read this as take the character at index I from the chars array, subtract from it the value of lowercase a, which will give us something in the range 0 to 25. That is the index in the counts array, and the counts array with an index is an integer, because that's the base type. We increment that integer. This compact piece of code makes solving this problem very straightforward. The only difficult part is to realize we're double indexing here. First into the chars array to get a value, subtract from it the base character A, use that as an index into the counts array, and increment. The re-encoding of the character value simplifies coding considerably. And this is where thinking through the problem well should help lead us to a compact, efficient solution. If we were to use chained ifs, which is a symptom of another type of failed reasoning, we would say if chars I equal A, counts 0 increment, else if char I equal B, counts 1 increment, all the way up to counts 25. We're missing the point if we do it this way. It's very hard to code, very error prone. It's harder to read and understand what's really going on, and it completely fails to use arrays properly. Notice we're hard coding the indexes. Anytime we hard code the index, it means either that we have one or two special cases or we don't understand how to use arrays well. We need to learn how to compute the index. The index is always an integer in a range 0 to number of elements minus 1. When we use arrays, we need to spend time considering how to do the encoding or re-encoding into the range the index values make sense for the array we're using. Often we can code a fair amount of power into a single line.